First of all, welcome to the 2022 abbreviated OpenSHMEM workshop. So first of all, I'd like to thank the UCF consortium for allowing us to sort of co-host and ride on the project that they were working on. I'd like to thank Oscar, Matt, Tony, and Pasha for doing the largest amount of work to get all this up and functional. Of course, again, thank the UCF consortium for co-hosting us. It is rather interesting because if you think about it, both OpenSHMEM and UCX/Open UCX have been co-developed for over a decade. So at least it's not far field and far-fetched from how they've worked together for a decade. We are planning on a 2023 OpenSHMEM workshop, so stay tuned. Where it will certainly be partially governed by pandemic, etc. But we hope we can have it in person. And I would say for those of you who are going or are going to at least go do the SE22 workshop meeting, you should pay attention to the BOFs because there's some interesting BOFs coming up that might be of interest to everyone. This was the original schedule, sliding slightly. We had two talks who were not able to make it. And one of them announced that this morning at about 0400 my time. So that was pretty cool. And so we'll slide everything back. I think we're going to start the panel session around 10-ish. It would be 10-ish my time, 11-ish yours, everybody else's. The panel session is not going to be recorded. I've asked that it not be recorded. And I'd like to give, we didn't get a chance to invite all the speakers we wanted to from the OpenSHMEM workshop that was originally going to happen. I'd like to give a shout out. You guys might want to check it out. Texas Tech has done a new version or a different version of the stream benchmark that they've actually published, and gave a talk at the HPEC conference, and it's in SHMEM. So they rewrote the whole thing in OpenSHMEM. I'd like to thank the sponsors as well as to Brian and Gabriella. And the sponsors, of course, are the Department of Defense, UCF, and Los Alamos. And that is, I'm now done sharing. So whenever you guys are ready to do your, the next speaker.
Well, we're still missing Aaron, it seems. But I think
I just got unmuted.
Oh,
okay.
Aaron. Okay, you're here.
Yeah, and I'm going to be displaying his slides. So just give me a couple of minutes so I can put them on.
Okay, fantastic.
Smooth sailing for everything, right?
Absolutely. So Aaron Welsh is from the University of Houston. He's going to be presenting Rethinking OpenSHMEM, Concepts for Better Small Message Performance.
Maybe, Aaron, you can introduce more about your history while I upload the slides.
Yeah, sure. And as a heads up, I forgot to make sure that the slide numbers were in there. So I'll probably be, making sure with titles that we're on the right page, but a bit of my history. So I started my PhD at the University of Houston a little while ago, in 2012. And I had initially started off with working on OpenSHMEM for Dr. Barbara Chapman at the time. Came up and started working in tandem with the Oak Ridge National Lab summer 2013, and kind of started developing a good relationship, going back and forth with them for many years. When in addition to the OpenSHMEM, I ended up working a bit on the predecessors of UCX, UCCS, and then UCX after that, and integrating that in the initial integrations with the representation. Also had some background working with some memory models and complex memory hierarchies, as well as kind of some dynamic and static analysis tools. Oh. And I can't see anything, so I don't know when the slides are up. I don't know how long I'm talking here.
They're up.
So...
They're up. I'm in the
Oh, okay.
first in the title slide.
All right, let's go ahead and skip to the next one then, the problem. All right. So as we all know, OpenSHMEM provides a simple and intuitive interface for SBMD communication that can map well to lower level hardware operations. However, we have a bit of a problem that comes in when we have an application that's producing large numbers of particularly small messages. Modern networks generally don't scale that well when you flood it with all those messages, and you can get degradation. So that's a particular problem for dynamic and irregular applications, like with graphs or data analytics and certain machine learning applications as well. So what we want is we want to be able to have a way to get better small message performance in classic OpenSHMEM, or as close to it as possible, so that we can still use the OpenSHMEM model we all know, but then still maybe gain the increased benefits. So next slide for the solution. Other efforts for addressing the same kind of problem in other situations often tend to focus on message aggregation. So we want to take all those different individual operations and defer them whenever possible, and get much larger numbers of them that we can then put all together into one larger message and send that out, and then we repeat that. But issues with aggregation is that generally it requires fairly substantial changes to the code for the synchronization model and data accesses. And as a result of that, it's rather cumbersome and difficult to write and maintain the code. And you lose some of the higher level thought that may be going into your algorithms. And so it'll look very different and no longer necessarily meshes well with your traditional access models. So for the next slide, we look a little deeper into the problem that we have here and why we have it. And when we think about it a bit, we realize that a lot of things can come down to completion semantics and developer expectations of what those mean for when they can access data in their program. And one of the key issues is trying to figure out how we can relax these and maybe gain some extra benefits from that. So much of this is kind of insufficient with what we have at the moment. So with the 1.4 specification, we got non-blocking puts and gets introduced, but when we look at it, we find that even that is too strict, because it's for requiring too much of the operation to be complete upon return. So we want to be able to take our code and define looser terms for what completes and when it completes. On the next slide. So to give an idea of what I'm getting at here, there's basically kind of two general levels of complete or categories of completion that we generally focus on. We think about the for the what, we have different levels, like whether the input buffers are reusable, whether an operation is actually posted to the network, or when the output buffers that you get back are actually complete with the values from the operation. similarly for the times, it can often be either when you return from the call, which of course we don't like here, or it's upon waiting on a handle or a secondary operation, at which point you have the question of what that might be, or if there may be multiple different kinds. So the next slide, we're going to be talking about the bail effort. So the bail effort exists to identify key challenges in access patterns and kind of provide demonstration for some different ways that can be used to address them. It does this by providing a package including a set of key applications of interest, showing different patterns or algorithms of interest with irregular patterns, and some libraries called XStack, XStack2, and conveyors that can be used to aggregate data, and then implementations of the applications in each of these environments so that you can compare how things look with traditional puts and gets or with one of those libraries and compare the performance directly. We will not be focusing on the XStack models, so we'll be focusing mostly on the conveyors models, the most recent iteration they have there, and how we can apply that under the hood within an OpenSHMEM extension so that we can stick more closely to OpenSHMEM principles while still gaining much of the benefits of the conveyor model. So on the next slide, we'll talk about what conveyors are and what they look like. So they're at the top level, they're kind of similar to message queues, where you can push messages onto them. They eventually get aggregated and as it progresses in the background and then pushed out to their destinations. And similarly, you can pull the messages that you may get from another conveyor on a different node and then process them. So they come with a set of operations and a set of different states, including what operations are legal in which states. So their states kind of work in a cycle starting from dormant, where the operations would be to begin working, reset, which is basically no up, or free it. And after you begin to transition to the working state, you can push and pull data freely, and you advance it with an advanced call with a parameter that's false so long as you still have data to push, and true if you don't. If you ever call it with advanced and then supply true, that's when it goes into the endgame status, and you can no longer push, but you have to still pull any data that's still out or getting received, and then continue advancing. And eventually, it'll progress to cleanup or complete, depending upon whether it's nearly done or fully done. And once it's complete, you can reset it with the reset call to start it all over again. So on the next slide, what conveyors are is that they're very modular, so that the API can be swapped out for different kinds of conveyor implementations. It's very portable and performance portable. They're efficient, which is of course what we hope for. Frugal with low memory overhead, and obviously highly scalable. So with them, we can get massive performance improvements for applications like these that have an emphasis on small messages. But the consequence is that they're very difficult to use, which we'll get into and see for ourselves. So on the next slide, we'll be talking about my extension, which I call conveyor context. So we want to be able to, like I was saying before, relax the completion semantics to make use of the existing concepts. And the 1.4 specification added communication context for a different purpose, but we find that it's a very a very good match to be able to start adding in these conveyors underneath a new kind of communication context. So additional options are, or flags are added to context creation so that you can signal whether you're trying to make a conveyor or conveyor context. And then when you later put and get on that context, you'll gain the, automatically you'll gain the performance benefits of the conveyors. But the operations, unlike the, it changes the semantics of the put and get operations that you're putting onto it, so that they're no longer what you're used to in normal OpenSHMEM. They're only guaranteed to complete, regardless of what it is, even the gets, if you call quiet on the context. So on the next slide, the extension that I wrote is implemented as a header running on top of underlying OpenSHMEM limitation, which makes it slightly limits some of the performance potential. So there's some room for improvement with that, but it carries the benefit that you can easily swap the underlying implementation between different SHMEM implementations with no changes, basically. And any time that we have conflicts that where I'm modifying an existing call, like with the quiet, I've implemented them just as instead as duplicate SHMEM X calls, so SHMEM X quiet, SHMEM X whatever, and the user then creates the context with the new option, SHMEM X context conveyor, and can then, again, with the duplicate calls, you can then do SHMEM X context put or context add, and they're available with no state management. All this previous stuff I talked about is out the window. You can just simply put and get to it, quiet, put and get, quiet. Eventually, you free it, and then it's done. So on the next slide, we'll look at an example of histogram in OpenSHMEM so we can see what this stuff looks like. So this is one of the Bail apps, histogram, that we'll get into a little bit later. And all it's trying to do is it's trying to update random locations in a distributed array. And this is what it looks like in traditional OpenSHMEM. And on the next slide, we see a bit of modification so that it uses the conveyor context. So the only differences really are the context creation at the beginning, which can be done more or less just once, basically. And then you have the atomic add call replaced with the appropriate SHMEM X context one, and then a quiet as in before the berry. And that's all that even gets changed. On the other hand, on the next slide, we see what the equivalent, even for something simple like histogram, what the equivalent conveyor code looks like if you just use the conveyor API directly. And it's much bigger, but maybe you think, next slide, maybe you think it doesn't seem that bad, right? Well, hold up. So we're only looking at the simplest of code snippets with that. So here we have something a little bit more complicated. This is, I think this was top of sort, but what the code is and does doesn't matter. If we go to the next slide, we see what it looks like in conveyors. And we change our mind. Maybe it is that bad. So we kind of don't want, so this big garbage thrown out on the screen, we kind of don't want to have to see this. And we don't want to have, obviously, OpenSHMEM developers have to actually write all this to be able to get the performance they need out of their code. So let's look at what, let's go to the next slide for the testing environment. Let's look at what this stuff actually looks like in practice when I ran it on some of the Bail apps. So I tested this on the Iris cluster from the HPC Advisory Council, the Dell 32 node cluster with 56 core Xeon 8280 CPUs. It's using the OpenSHMEM 1.4 from OpenMPI. and UCX 1.12 is in there, compiled with GCC, and each test is run on 2, 4, 8, and 16 nodes using combinations of 1, 2, 4, 8, 16, 32, and 56 processes per node. So the next slide. Now we're going to go back to that histogram. So like I said before, it's it's representing a communication pattern where you just have asynchronous and irregular updates to random locations. So the test, all the test does, as you saw, was that it generates, before that part, it generates a uniform list of random indices to that table, and then in the course of the test, it just simply goes out and increments each one. So on the next slide, we see what this actually looks like for the performance when we run it. So that AGP version we looked at first, those are the red lines here, and we can see so the conveyors are green, and my extension with the conveyor context are the blue lines. And so we can already see, even for something simple like that, how drastic of a performance difference it can make, especially as it starts getting more congested. At the start, it's like, okay, it's a 10 times difference, who cares? But you start to really feel the impact once you start congesting the network. So this is great, but let's look at the next one. So next slide. Index gather is the next Bell app we're looking at, and it's rather similar to histogram, but instead of asynchronous writes, we're doing asynchronous reads from random elements. So you generate the same, similarly, you generate the random indices, and then perform get operations on them one after another after another. I did make one small modification though from the Bail on the Bail version of the code on GitHub, since they use the older gets and we now have non-blocking gets. So I thought that would be a slightly better comparison. But on the next slide, we now see even with that, that it still makes a drastic improvement to be using the conveyors. It's not quite as bad at first, maybe as the previous one, but it's still just as critical. And we do see some slight overheads from the conveyor context, but the goal here is to be at a acceptable level, and this qualifies. So for the next slide, looking at one more test, the sparse matrix transpose. So it's computing matrices in the compressed sparse row format, and then trying to do the transpose of those, which is useful for many machine learning algorithms and data analytics. But the problem is, and this is why this is in Bail, is it's rather difficult to aggregate the data due to the synchronization necessary for determining the locations of where things get swapped to, and then writing them out. So there's some locking involved to acquire the locations before writing things out, and you having to wait. The same kind of dependency aspect I was getting into. You're waiting on the completion semantics of calls to be able to move on to the next part. So we don't like that. But there's two phases to the transpose. The first uses a histogram model to just determine the number of non-zeros for each column, so that you can then make make sure the distributed arrays are the right size. And the second phase then goes out and acquires each of those values to determine, it fetches the information for where it needs to write to, and then it actually performs the write. The conveyor context implementation, however, does an operation similar to loop fission. So that second phase gets broken up, and we have a sort of buffer where we go out and fetch a whole bunch of values at once, and then we store them away, and then those can get aggregated separately from the next part of it where we actually make the updates. So the next slide shows the results for the sparse matrix transpose, and it still looks pretty good. It's only a marginal drop in performance over conveyors, and gives us substantial increases over traditional OpenSHMEM. And all it took was just a little bit of a loop vision at that one point and using the context. Okay, great. So next slide. So the conclusions we can draw from this is a slight decrease in performance, although there is, as I mentioned before, there is plenty of room still for improvements to make it even better. But it's a small decrease, and it allows us to write the code in a much more comfortable fashion. So that looks great. But what if we have something that's a little bit more complicated than those? Enter the next slide. We have TopOSort, the golden goose. So the reason why those three particular apps were chosen is because they basically lead up to TopOSort as components of it. Since within it uses all three patterns. So TopOSort starts by creating a unit upper triangular matrix, applying random permutations to it. And the goal is to create row and column permutations such that when they're applied to M, the result is an upper triangular matrix. And we saw some of the code for it earlier. So it's much more complicated, but it has substantial potential for performance improvements. The initial atomic guess input implementation, I believe, had sometimes as high as a 40 times performance improvement to go to conveyors. And this application is also great because it's precisely because it's so much more complicated and puts all the different patterns together. So it's great for demonstrating the flexibility and utility of the aggregation model. But next slide. When we're looking at that, we can start to see a little bit more what the conveyor contexts lack. Once we get into something a little bit more complicated, we realize that we can still get stuck on interdependent operations, and the interrelationship between them is a little bit more complicated. So we can't just as easily, do something like the fission and get the results we want. So we go back to thinking about those completion semantics again. So we want to be able to find a better way to get control over those and be able to convey that information to the OpenSHMEM implementation so that it can do a better job of more appropriately making sure that certain operations can be combined together so we can still get them processed in bulk. And to that end, my current work is proposing sort of duality of additional changes. One in this form of something akin to futures and promises, so that the results of a previous operation can basically be given as a future that you can just pass to a subsequent call, and it'll allow it to evaluate that later when it's actually getting processed. And that can allow us to put some more of them in bulk. However, we can still have interdependencies with other code lines that aren't OpenSHMEM calls. So the other part is a form of tasking API. Neither of these is necessarily quite exactly what a full API would normally look like, but it's along that vein. And you have the ability to create the task and then put those tasks onto the conveyor context so that they'll execute them later on. And then that way you can allow yourself to be able to have deferred execution of dependent code blocks as well as network operations. And next slide. So with that, the future work is of course working on some of the tasking and future features for completing top of sort. It's also using only the very simple private, single-threaded model. So the thread models that we see in 1.4 context creation can't all be applied. They're not all compatible with conveyor context, although they could be. And potentially also directly integrating into an implementation for even better performance. So I think I'm running tight on time. So I don't know how much time I have for questions.
There was a question in the chat from from James. Said, I didn't catch an advanced operation in the context conveyor. How is this accomplished?
I'm not sure if I follow what's being
Asked.
referred to as an advanced complication, as an advanced operation.
Hey, I can come off mute here. I
there
guess
you go.
since I have a mute button. Well, so in the conveyors programming model, there's this advanced operation, right, which is used so that you can consume data that's been sent over to your local process, right, so that you can free up buffering space in the conveyor so additional data can move.
Oh, yes.
Right, so that was the thing that I was thinking about. Maybe I missed it. I was just didn't quite catch how that would work with the context approach that you were talking about. Yeah, no, I didn't realize you meant advance as in that advance. So yeah, I'm on the same page. So basically, that's part of the progress model, and you're wondering like how and when do things progress? Well, they can. So the implementation, or my header in this case, will have its own progress model it runs, where it'll still be advancing it within its code, but it's hidden away from the user, so you don't have to advance it yourself. It'll advance on its own. Does a follow-up question? Oh, I'm sorry, Aaron. A follow-up question is how does the application define the operation that should be performed on an element that gets received? Is there a callback that's given or something like that?
No, there's only a select subset of different operations we can have in the first place. You know, you're either performing an add, or you're performing a get or an increment or whatever. So it's basically is stored as like an enum. You have, and maybe I should have had a few more details of the internals to show what it looks like, but basically you have packets that you're sending as your messages to on the conveyor, and as part of that packet you have the enum saying this is the operation type, like it's an add, and here's a value that goes with it, say 4, and then you have as part of the conveyors API itself, you have a destination. So with all that, you can basically process that, and you each time you're getting something off, you're basically getting that packet and you read it to find out what you're doing. Does that answer your question?
Yeah, that was great. Thanks.
Are there any other questions?
No, thanks much. I appreciate it. That was good.
I have just a very few question, a short question. How you stated that the original goal is to stay as close as possible to the atomic get and put programming style of the book, and as you add basically this extension, and later on you mentioned features and promises. How far are we going? Are we getting away from that original goal? Do you see that that we're heading in the improving to reduce the complexity to the user?
So you mean You mean you're referring specifically to once not the stuff we were talking about for the first 3 apps, but once we start talking about the futures and promises and the tasks for doing things like more tough, complicated stuff like top sort, how much that might represent the departure. That's the question.
Yes.
Well, it's definitely a slightly larger departure, but it's not necessarily that it's not that great of one either. So with traditional OpenSHMEM, if we're trying to do something like, the easy example is you want to do a get, and then say you're getting a remote destination address. So you perform a get, you get an address, and you use that address to determine where you're sending some data or it's a value or whatever, and then you put that out somewhere else right afterwards. So you do the get, you do the put, and that's the typical way, right? Well, all that changes for the futures thing is that instead you perform a get, and instead of a buffer containing the value, you just get an object that will contain the value, and then you still, like before, you just turn around and then put it to the network, and it'll resolve it on its own. So in both cases, it's basically just a value. The only time it changes is if you try to, in a more substantial way, is if you try to get a value and then immediately use it locally. Like you want to just read the thing directly. And at that point, you would have to have a call to specifically wait on the future. That is, I think that's a little bit different, since we don't normally have ourselves waiting on individual operations within OpenSHMEM, but I don't myself view that as a very serious thing. And then for the tasks, it's kind of similar, where the idea is basically it's kind of like a copy pasting, at least for the way it's implemented. So, before you might have some for loop, and then inside the for loop you have another for loop that operates off of data you got from some get call or whatever. Instead, if you just had that for loop as a helper function, that would still be normal SHMEM. But now you take that instead and you make that helper function be a callback, and you put that the reference to that function as the value for a put operation to the conveyor. And that's basically tasks. That's what I have for that. And similarly to the futures, I don't personally feel like that makes it all that harder or less OpenSHMEM-like. So that's kind of why I was pursuing those angles. It seems to me like it makes sense, but obviously it's a subjective thing.
Sounds good. So going to be looking for.
I'll make a shout out. It was slightly different and more proper to the concepts than my futures and task-esque implementation here. But once upon a time, there was async SHMEM that kind of looked a bit into what it might look like to add those to OpenSHMEM as well. So just a bit of a shout out with that.
Thank you, Aaron. Looking forward for your updates, and thank you for presenting your work.
Yeah, my pleasure.
Next, we have a QoS-based interface for taming tail latency. I think that's Manju and Vishwanath.
I'm here, so let me share my screen. Let me know when you guys can see my slides. Hello?
Not yet. We can see your name, but not your slides yet.
Interesting. I did share my screen.
I'll say it is Zoom. There you go. Now you're in, you're in,
Sharing the wrong screen.
yes.
Okay. How about now?
Ah, awesome. Thank you.
Okay. Good morning, everyone. My name is Vishwanath. I also known as Vish. Um, I'm also from University of Houston. I graduated from University of Houston back in 2013. I've had a stint at Intel before joining NVIDIA recently. Now I'm working with Manju, and I'm here today to talk about improving QoS for OpenSHMEM applications using in-network priority, specifically in NVIDIA InfiniBand architecture, and using QoS-based interfaces. So before I jump into the details of the talk, I'll just give a brief motivation why QoS QoS or quality of service is important. QoS refers to the ability of a network to provide better service to a selected network traffic. Achieving a good quality of service for short messages under a high load in a shared cluster is a desirable characteristic for a HPC application in general and OpenSHMEM applications in particular. So a congestion can be experienced in shared HPC systems due to contention for resources such as shared networks and IO systems, etc. And these can create adverse user experience and can impact the overall system's performance. And also with increasing core counts on leadership scale machines, exclusive access for any program execution will be rare, and this problem of contention is only expected to exacerbate. So a network congestion is one such type of congestion caused due to contention on network resources such as switches and HCAs, and these can typically lead to prolonged tail latency in most scenarios. So in this work, we focus on studying and how to achieve shorter tail latencies for short messages in OpenSHMEM. Specifically, we're going to use a feature in NVIDIA InfiniBand hardware called virtual lanes. We are also going to expose the QoS prioritization to the users through the newly proposed OpenSHMEM queues API, which was originally designed and proposed for supporting aggregation of messages in alignment with the previous talk, and we will get into the details of the API as I go through the talk. Although this talk is primarily focused on the QoS aspects of it, I will touch upon the aggregation parts of the OpenSHMEM queues API as well. So so this is the general agenda for the talk. We'll look at how to define tail latency. We're going to characterize QoS with the help of this metric, and then we're going to I'm going to talk about the measurement strategy that is going to be used to extract this tail latency. And then I'll talk about the design and implementation for the interfaces that were used to achieve this, starting from OpenSHMEM and all the way to UCX, and how we achieved overall improvement. I'll talk about a little bit of experimental evaluation and discuss some of the ongoing work and future work in this talk, and conclude it. Okay. So tail latency can be defined as a small percentage of the transfer times in a system that take the longest compared to all the bulk of the transfers or all the samples that are in there. So what that means is that a tail latency value represents that all values a tail latency typically is the 99th percentile latency or P99 latency. So which means it marks that 99% of the samples are either faster than or equal to that P99 value. And network congestion can be characterized with the help of tail latency because contention in a shared resource, shared network resource, can cause the tail latency to be extended. So in order to measure tail latency, there are multiple approaches to do that, and most benchmark use an approach called the HDR histogram, which is the high dynamic range histogram. And one benchmark that does that is also GPCnet. GPCnet is a benchmark which was developed for MPI, which measures congestion by running multiple types of communication with some congestion patterns at the same time. And they use HDR histogram methodology to extract the tail latency and then finally the congestion impact factor. So to measure tail latency and congestion impact in our work, we leveraged the essence of the GPCnet benchmark, and we created an OpenSHMEM benchmark based off of that to measure congestion with OpenSHMEM APIs. So the idea is to take this benchmark and introduce OpenSHMEM style tests like an RMA put, RMA get, and atomic add instead of point-to-point operations that that GPCnet uses. So just a quick primer on how GPCnet does and how the modified version with OpenSHMEM really operates in this case is that the benchmark, when it starts with all the P's are split between two types of tests, so what I call as a network test and a congester test. And if it is a congester P, then it would go ahead and run an all-to-all congester benchmark, which was written inside the benchmark itself to maximize congestion. And then if not, it would go ahead and run the RMA operation that the user wants to measure congestion for. So it's basically running two types of operations simultaneously in two different parts of the same set of P's that were launched. And eventually the statistics is computed and histograms are generated, and finally the P99 tail latency values and the congestion impact is all calculated and then reported. So that's basically what the benchmark does. So we just saw about what tail latency is and how we're going to measure it, and now I'll talk about what approaches that we are going to take to mitigate that tail latency. So the primary goal of this mitigation effort is to provide selected traffic to provide controlled latency, right? So in order to provide users for controlling such priorities with OpenSHMEM API, the API must be able to interact with InfiniBand hardware through the UCX API underneath the hood. So before we dive into the details on the software side, brief primer to some of the InfiniBand architecture's QoS hardware features used in this work, specifically with respect to service lanes and virtual lanes. So the InfiniBand architecture hardware does include quality of service features. Has been there for a while, and the InfiniBand architecture's basic unit of communication is a message, and messages are segmented into packets, and all IBA packets contain what you call as a service lane information in their local routing header within a subnet. Let me take a laser pointer. Okay. Local routing header within a subnet. There is a SL value directly present there, and then also in the global routing header across subnet, which is present in the T-class field. I think most will be familiar that the IBA utilizes a logical endpoint called a Q pair, which is on the host side of the host channel adapter. The port side of the channel adapter implements what we call as a virtual lane. And the virtual lane enables multiple independent data flows to share the same link. So a set of HCAs connected together is called a subnet. So now the assignment of the service lane is a function of the communication manager of each of each node, and its negotiation with the subnet manager of that particular class subnet. So the SL to VL mapping between the subnet manager and the HCA is what will enable QoS implementation on IBA. So this is sort of a high-level explanation of how the hardware really enables us to segregate traffic, and we will be leveraging this feature in the hardware to express priority using OpenSHMEM and UCX. So that's with respect to the hardware concepts that are available to segregate traffic. And now we'll talk about the API that we're going to use. So I want to talk briefly about OpenSHMEM queues here, and again, I can talk about it after we present the results for the QoS work, and we can talk about aggregation again. So the OpenSHMEM queues API it was developed for enabling communication and data aggregation. And we know even from the previous talk that communication and data aggregation is known to provide better performance characteristics for PGAS and OpenSHMEM applications. Although there is not a clear abstraction that is available at this point that can be used by the application to express such kind of aggregation intentions. So that is where the OpenSHMEM queues come in. The OpenSHMEM queue is an opaque object where the users can interact with the queue only through the OpenSHMEM queue interfaces only. And it has different types of queues. It has the communication queues, data queues, and what I call as the priority queues, which is what was used in this work. So communication queues are used for aggregating communication operations, data queues for enabling aggregation of data before sending the data to the destination PEs. And also the different goals of the API was to keep the underlying mechanisms agnostic so the aggregation to be agnostic of the underlying mechanism and the agnostic of the thread or the PE posting the operation. A detailed API proposal that has been published for the OpenSHMEM specification has been published, and the link is available here for everyone to look at. So I don't have all the APIs of the OpenSHMEM queues here, but rather I took a snippet of it, only those that is relevant to the QoS work that is presented in this talk. So one of the key reasons is that I wanted to highlight what modifications were added to the proposed API spec to add support for QoS. So basically, I'd added a new type of queue and then a new class for QoS, which allows you to segregate traffic based on different types of priority. And the APIs for communication queues, wherein there's a queue create and a queue destroy, followed by a queue push, wherein you can push different types of communication operations. Currently, no collectives are supported according to the architecture, but we have the architecture intends to support put, get, and atomic operations through these APIs. And then we have a progress call to progress those operations, and the buffers can be considered to be reusable once there's a flush call made for that particular queue. So in the context of the QoS operations, each queue can be thought of as a different priority and can be created at the beginning of the application and be alive through the lifetime of the application. And operations can be queued in and that needs to be run at a certain priority, based on how the user specifies those priority, the hardware will automatically prioritize those transfers with the appropriate cadence. So we've seen how we're going to measure the performance, measure the tail latency. We've also seen how we are going to expose this to the applications. So we have the application and we have the interfaces, and I'm going to talk about how we accomplished it throughout the entire software stack, starting from the application to UCX. Until the subnet manager itself. So one of the key things that we need to know, as I mentioned when I was explaining about how SLs work in InfiniBand architecture, is that it is a negotiation between the connection manager and the subnet manager, right? So the subnet manager must need to be aware of what channels need to have higher priority. Like take a look at the typical subnet manager configuration here, where you have an SL to VL mapping, where I think the position represents the SL and the value represents the VL. So here SL0 maps to VL0, SL1 maps to VL1, and SL2 maps to VL2. And we are specifying here by a VL arbitration value, saying that the VL1 will have the highest priority, whereas VL0 and 2 will have lower priorities comparatively. So theoretically, when we run an application, we create two different queues, for example, and one queue we can set as high priority and one queue as low priority. So the synthetic benchmark would create those queues and enqueue the operation that needs to be run at a higher priority with the higher priority queue, and then operations that need to be run at a lower priority with the lower priority queue. And inside UCX itself, this queue value is being translated through the worker parameters. So basically, each queue's value, each queue's quality of service information is provided through the UCX worker params, through which it is sent all the way to the UCD layer to select the appropriate SL. So, so each packet has its all their SLs that is sent from the application through the OpenSHMEM queues API through the UCX worker, and the SL already has what has to be done for those priorities with respect to the VLs, which VL has to be prioritized. So with this information, when we can run an application here, we should be able to segregate traffic and then isolate traffic of importance and traffic that is not important. Specifically, in this case, in our study, we're going to consider the congested traffic as the non-important traffic, and the RMA traffic, which is the short message traffic, which is what we want to prioritize and speed up and reduce the tail latency. So that will be the focus on this one.
Yeah, pardon me, Pasha has his hand up. I think he wants to have an interactive question.
So, sorry?
Pasha has his hand up, and I think he would like to have an interactive question.
Oh, sure.
Pasha, feel free to speak up or unmute yourself.
Maybe Pasha can't unmute himself. So Brian
Be
would
a
have
mistake.
to. Yeah. Okay, just continue and we'll catch up later with Pasha. Thank you.
All right, sure, no problem. So for the experimental evaluation, I'm thankful to the HPC Advisory AI Council for offering the IRIS cluster, because we needed to make a custom subnet for this particular experiment. And we used the IRIS cluster like what Aaron used, and we had exclusive access of this cluster for the subnet manager for the measurement, wherein we were able to set the subnet configuration appropriately. Okay, so to show the impact, we wanted to do a P99 latency comparison, and we wanted to measure the congestion impact for the P99 latency. We want to compare P99 latency congested and P99 latency baseline. So we run the RMA benchmark, and then we get a baseline P99 latency, and then we run it with a congester simultaneously, and then we measure the P99 latency, and then we run the same benchmark with the QoS mitigated approach, wherein we send the RMA traffic through a high priority queue and then the congested traffic through the low priority queue. So the results are shown here, where we can see the blue bar is the congested value, and the congested scenario and the congestion impact for that. And then the orange one is the QoS mitigated part, where we have congestion impact for that, and we can higher is bad and lower is good, and we can see that with QoS mitigation in almost all scenarios, we are able to reduce the congestion impact quite significantly, even more than half in many scenarios. So this is sort of a detailed histogram of one of those operations, where we can see that the baseline put is shown up there with 1.1 and 1.2 microseconds, which is sort of normal. But when we really congest the network, we see there is a big impact in the P99 latency that goes up to 8 microseconds. And then when we are able to mitigate the QoS by sending those put operations through a high priority queue, we can really reel it in to 2.2, which is not as good as the baseline, but at least it's not is quite very close. That's the idea, to be able to do short tail latency for short messages, even with high load. So that's with respect to the queues work. We've talked about that. So I just wanted to give a quick overview of the aggregation work with the OpenSHMEM Queues API. That's a work in progress at this point, but I'd like to talk a little bit and then give a brief early results overview of this one. So the batched RMA operations or aggregated operations, it does lead to high message rate and bandwidth. We've already seen even from the previous talk, and the Bale package conveys demonstrate the importance of aggregation of a message for message rate. I'll just dive into the implementation, and we've already seen the Queues API before. With respect to the implementation, there are multiple approaches to achieve aggregation. And the first approach that we are trying right now is to use post list for the verbs API. And there are, of course, other options, but we wanted to start from there. So we have a current working implementation using verbs post list based aggregation, where we can merge worker requests by passing list to the IBV SG structure. So with respect to UC exchanges itself, we didn't. There wasn't a lot of changes to the UCP API. We sort of worked around right now to use the IOV data type in the UCP put and get NBX calls, and then pass an IOV list of buffers instead of a simple send receive buffer. So the RC verbs provider is used in the UCT layer. So at this point, that's the only provider that will work with the implementation. So inside the UCT implementation, we construct a SG list based on the number of worker requests submitted from the Queues API, and then once we construct the SG list, we are able to post it through IBV post send and take advantage of post list and reduce a bunch of doorbells. And so that's the sort of the first take implementation right now. We're still improving this and work in progress, but yeah, that's where the implementation currently stands. Again, we tested it with the Iris cluster in the HPC advisory council machines, and we were the OSU benchmark for message rate was modified to use the communication queue APIs, which was fairly straightforward to do that. And the threshold for aggregation is currently set as an environment variable that can be passed through while running the during the launch time of the benchmark. From our tests, currently we can see that there is at least 2.2x improvement in the message rate scalability. So in case of no aggregation and with the threshold of 2, and then comparatively with the threshold of 4. So as we keep increasing the threshold, we're seeing better aggregation. We are going to do a higher threshold test, and we're going to sort of stabilize the implementation and improve it even further as we move on. But that is currently the state of the of this work at this point. With that said, Okay, so I have one more slide. So there is a summary to summarize everything. Congestion and under heavy load does have a very big impact on the application's performance. So OpenSHMEM priority cubes help short tail latency even with congestion. Our results demonstrate over 2.5x reduction in tail latency with our approach. So the OpenSHMEM queues API provides a neat abstraction for QoS. It allows user to prioritize communication traffic from OpenSHMEM application even when there are ordering concerns. And it also enables portability, right? So you can the queues API abstracts out other future potential mitigation approaches in hardware that could be added. Like, for example, there could be potentially telemetry aware congestion mechanisms that could be added. And we are looking into cache stashing as a design point as well. But those can be completely abstracted out from the user while using that. So the ongoing future work, we're going to continue improving message rate with better aggregation mechanisms for OpenSHMEM queues, stabilize that implementation, support OpenSHMEM data queues for aggregation, and that support has not yet been added. That's something that I'll be working on in the near future, and also explore offloading opportunities for the OpenSHMEM queues progress and aggregation, like, for example, offloading to the DPUs as one case. I think that's all I had with respect to slides. I see there is a lot of chat there. I can take questions right now.
Yeah, it looks like there was some ongoing chatter between Pasha and Manju, but I think that was all answered.
Okay, yeah. So yeah, the SL, we've modified the UCP worker interface, like Manju mentioned here. So yeah, that's not upstreamed yet. That's correct.
If any of the attendees do have questions, they can use the Q&A panel at the very bottom of the screen, or they can type something in chat. We're monitoring both. Let's just give it a moment.
Sure. Oh, I just realized I never scrolled down the video. Sorry.
Yeah, it's okay. Yeah,
Do
Vish,
we
I'm
want-
not seeing anything. Is anyone on the panel have any questions?
No, one quick one is the changes that you've made to UCX. Is that I'm assuming you guys are going to test it out before you fully upstream it to make sure that it doesn't potentially break something, which would be a bad thing.
Yeah, absolutely. Yeah, I think it will go through proper channels before we upstream it.
Okay.
And ensure that yeah, we'll run it by the UCX team before we
awesome.
upstream it. Yeah,
That was my only question.
sure.
I can't enter in the chat, but if I could maybe enter in here with a question. I don't know if
Yes.
I'm still unmuted. So I'm kind of a little curious. So it was just mentioned about things breaking. Since this is a lower level interface, I'm kind of wondering what the expectation or approach might be for long-term stability of the API or things that would be written with it, for anything that may change with any of that stuff that might potentially break code.
So you mean the UCX changes?
Yeah.
Yeah, I think that the change for UCX is just an additional parameter to the worker params. So all the use of service lanes already exist in UCX at this point. And what this particular work really does is to sort of expose it so that the OpenSHMEM APIs can really access it. So whatever the service lane usages that needs to be done, that has already been upstreamed and that exists in the InfiniBand UCT layers already. What this one is really doing is just passing on a single value from OpenSHMEM to UCX. So that's why I didn't really dive into the UC exchanges, because there is not a lot for the SL work alone. I mean, for the aggregation work, sure, there is a lot more changes, and I think there will be a bit more rigorous process in ensuring that we do proper testing and upstreaming. But for the SL QoS work, the changes are minimal.
Maybe I can add, Vish.
Mhm.
I think we also have to, we have a proposal in the OpenSHMEM community to have OpenSHMEM queues, right? So once we kind of have a progress there, right? We'll also working on what the UCX interface for the SHMEM queue should be. So in a way, it's kind of coordinated. We don't want to make we don't want to propose multiple changes. We want to figure out whether queues can give us both QoS and aggregation, and that's the direction we see makes sense. And so far, our results also support that. So in a way, we want to keep one change, and that one change will to the interface would likely be, or we wish it's going to be OpenSHMEM queues and something like UCX queues. So we are experimenting now. Once we figure out a right interface, that's what we want to push. I mean, I think the concern is not too much about how this can be implemented or so forth. We want to figure out right interface first, and so forth.
Jim seems to have a question.
Yeah, I'm trying to figure out how to phrase this question. So as we're talking about small message aggregation, message queues, conveyors, things like this, I think the question that I have in my mind is, why are RDMA writes the correct communication model to build this on? Right. I guess what I'm wondering is, if we were to use sends and receives, the destination would get an event when right from the communication layer when data arrives. Is there an advantage? Is there an advantage to using one or the other? Right, in a sense that, this is enough of a departure from OpenSHMEM that I'm kind of having, the question of, why do we build it on top of OpenSHMEM? What's the advantage? How do these things fit together? Open question for Manju or Vish. I'm just really curious to hear, what your experience has been.
You mean for the queues or in general?
I think, my question is maybe about this, is maybe more general than this work. But I am interested to hear an answer in the context of the work that you've done.
I don't know. It's kind of like I don't know, like if there is a pointed question, rather it's an open question, right? So I mean, the RDMA obvious advantage is you decoupling the data movement with the synchronization, right? This obviously has an advantage. And you don't have your target to be active. It's a passive target, right? Exactly, gives you an advantage, right?
Well, that's a difference with aggregation, isn't it? That the target is not entirely passive, right? The target has some obligations in most of these aggregation-based approaches, or is that not the case with the work that you guys have done?
So far, what you have done, that's not the case, right?
Yes.
For example, right? Like even say that some hardware element or a progress thread does this, the user is still agnostic. The user is not we are not expecting the user to do call progress on the target site. That's not our intention. So we will have some passive targets still.
If I could step in for this question a bit as well. I mean, think of for your question on, if, you're implicitly making the other side more active. I mean, a simple scenario, just think about when you're talking about aggregating a whole bunch of puts. You're at, the only thing that the sides that were active, that would have been active before, are still only the ones that are going to be active now. If you aggregate a bunch of puts, all you're doing is just deferring them. You're not making the other side do anything in response. You're just simply doing a bunch of puts.
I'm assuming
well,
there's some disaggregation, or that's not a good word to use, I guess, but deaggregation that has to happen at
Yeah,
the
it's sort
target.
of a scatter.
there's a little bit.
Yeah, but I think that's like Manju mentioned, that would rather be passive, and at this point at least we don't expect the receiver with the queues API at least. I don't expect the receiver to do any progress.
I guess it's really about from the perspective of the sender. That's what you're focused on. And also, I would add that how many times have you tried to ask someone to rewrite their code in a different model because you think it should be used in that
I'm
model?
not suggesting that we change the programming model. I'm just kind of pondering the underlying implementation for these things, right? If it's so if the deaggregation is dealt with by the NIC at the destination and we don't need a temporary buffer, then that's great. I think my question disappears. But if we do need to place data into a temporary buffer and then do some deaggregation on it, or in the case of conveyors, if there's some processing that needs to be done as part of that deaggregation, I think the question I have is, are we using an RDMA write because it's available in OpenSHMEM, or are we using it because it's the right underlying mechanism? And when I say send receive, I'm not thinking of an MPI send receive. I'm thinking of an RDMA send that an InfiniBand NIC would do, right? There's no matching. It's still an RDMA, right? It's just that the semantics are, that it lands into a receive buffer instead of a memory registration.
Okay, I think I understand your question better now. So my easy answer would be like, if you have something like a DPU, you can still disaggregate completely most cases that I can think of on a DPU. So you're still doing on the network.
The DPU, you're having the ARM cores do it?
ARM cores it can run OS, right? So it can do what you want.
Right, but in that case, wouldn't it be advantageous to post a receive buffer? Right, because then the notification of the data arriving travels with the data.
Sure, but why do you want to post a receive? We can get away with not posting the receive, right? Because we have a symmetric address, we have source and destination buffer, and we can still maintain the PGAS model that we have, right?
Right, but I mean, I guess the other part of what I'm thinking through is how do we manage this intermediate buffering space that we're using for the aggregated message? And it becomes the sender's job to do that, right? When you're using one-sided communication.
I think we are striving towards not having an intermediate buffer. I don't have an answer still because we are exploring that part, but what we are striving is not to have that intermediate buffer.
Okay, yeah, and like I said, I think if there is no intermediate buffer, then there's no agent that needs to be notified, and my question kind of vanishes. I was thinking of those cases, where the implementation does need to use some intermediate buffer. I mean, maybe it's more, maybe the question is more relevant in the context of like the conveyors work that Aaron presented.
I think you're right. It's right. In data aggregation, we need some kind of an intermediate buffer. That part we haven't explored yet. So I don't have a good answer to be, or not like, I don't have a concrete answer yet. So, but I would say that our goal is to not have a intermediate buffer, ideally.
Okay, yeah, thanks. I appreciate the discussion. Aaron, I didn't want to cut you off. I didn't know if you had any closing thoughts.
No, not really. I kind of jumped in the first place. It wasn't my talk time already, but no, we're good. It was the same thing. Your clarification on the one-sided versus two-sided part was kind of the big point where we were not on the same page. So yeah, no, it clarified everything for what you meant.
Yeah, thanks. I mean, we have this two-sided thing that the NIC can do, right? And it's much simpler than what an MPI two-sided looks like. And that's what I was thinking of. Okay, I will yield the floor back to Vish. Thanks for taking my question.
So are we done with all of the questions at this point? Do we want to move on to the next topic, which is a panel discussion? Does everybody agree with that?
Yes.
Do we have everyone here for the panel? We did have set up a break so everyone could make it at 10 o'clock for the panel.
Yeah. So we can maybe have the break and then have everybody join in, I think it's in 25 minutes for the panel.
Just a short break, yeah, until 10 a.m. Pacific.
Works for me.
And we'll stop recording, and yeah.
Thank you.
Look forward to seeing you in 25 minutes.
Thank you guys much for the talks. I appreciate it. I'll see you at 10 Pacific.